So where things start to get interesting in climate science is when you start putting the pieces together, because they interact in ways that you might not anticipate right from the outset. And the way they do it is by means of feedbacks. So a feedback is a loop of cause and effect. So there are two different kinds of feedbacks in general. There are positive feedbacks, and there are negative feedbacks. So let's say that we have a thermostat in a house, and it's controlling the temperature of the house, and it's got a set point that's sort of right there. And then something happens that makes the house too warm. The response of the thermostat, in this case, so this is a positive perturbation. It's too high. The number is too positive. The response of the thermostat is to push it toward the negative. So a negative response to a positive perturbation. So this is an example of a negative feedback. A negative feedback is a stabilizer. A positive feedback, on the other hand, would be if you had the thing wired backwards or something, and if the temperature is hotter than it's supposed to be, if that, for some reason, provoked the furnace to make the thing go even hotter, that would be a positive feedback. Or if it was too cold, and that, because your furnace was broken on a, crummy day like today when it's raining and nothing seems to be going right, a negative feedback would tend to make, a positive feedback would make, if it's too cold, it would make it even colder. So a positive feedback is an amplifier. There, yes?
What's the set?
Like the thermostat temperature, okay. The set point. You know what you set the thermostat to. So, another way to imagine or to describe these feedbacks is to imagine a bowling lane. So let's say we had a bowling lane that was a fiendishly difficult bowling lane, and it was kind of bowed up in the center. And your job is to roll the bowling ball right down the center of this thing and hit the pins that are down here. But the thing is, the lane is sloping downward on both sides. So if you're off just a little bit, it goes off even further. It makes it very hard to bowl in such a lane, because there's a positive feedback here that amplifies any screw up you make. If you're not quite right, this thing is going to amplify your error. Whereas if you had a bowling lane that was nice and benevolent and had like a trough in the middle, like for a kid's birthday party or something, if the thing is out of true, it will tend to get pushed back toward the center. So this is a positive feedback here and a negative feedback here. So a negative feedback is a stabilizer. Positive is an amplifier. So we've already had seen some examples of negative feedbacks in the class. One of them is the Stefan-Boltzmann. The way that an object radiates away infrared light as a function of its temperature, and it sort of finds an equilibrium temperature that way. So IR emission is a negative feedback. And there's a way that I wrote them in the textbook that seems like a useful way to sort of think about these things. The thing that is being stabilized in the layer model when you're letting it find its equilibrium temperature is the temperature. So we'll write the temperature as the variable that's being fed back upon, and put it in a box to make it look snazzy. And then we're going to perturb the temperature by something. And so you make the temperature go up a little bit or down a little bit, you're perturbing the temperature. And then there's this sort of loop of cause and effect, which has to do with the infrared energy flux. And so if you make an object hotter than the equilibrium temperature, like the layer model or the planet Earth or something like that, you get more infrared energy leaving to space, and that is a negative feedback. So I put a minus sign right here, and then it's sort of a loop of cause and effect. Or the sink analogy is another one. So here, the variable that's being fed back to is the water level. And so we've got the sink, and let's say that you've had the faucet going for a long time, and the water level has found its equilibrium so that it's dumping as much water down the drain as is coming in from the sink from the faucet. And then you take a bucket and you dump a bunch of water in there. That could be a perturbation to the water level. Or maybe you scoop in there and get a bunch of water out of the sink. Either way, you perturb it somehow. And then the flow down the drain is the loop of cause and effect that makes a negative feedback here. So, there's nothing new in this. You sort of digested these ideas already, but we're just sort of putting it within this framework of this loop of cause and effect. But the killers in climate science are the positive feedbacks, because they can take a climate perturbation, like from fossil fuel CO2, for example, and they can make it worse by making a positive feedback. So the simplest of the feedbacks to understand that sort of act in climate science is called the ice albedo feedback. So ice is very shiny stuff. Snow, in particular, sea ice is very, very reflective. If you melt sea ice, what you expose is the water underneath. The albedo of water in the ocean is extremely low. That means that sunlight that hits the ocean gets absorbed. It doesn't get scattered back very much. Whereas the sunlight that hits sea ice, if you actually have sea ice in the sun, then it's very shiny, and so it reflects back. So the ice albedo feedback operates on the temperature. And the loop of cause and effect is that ice melts or freezes. And this is a positive feedback, because if you warm someplace up that has ice, and then the ice melts, So now the sunlight gets absorbed instead of getting scattered back or reflected back out to space. That causes it to warm up even more. So this is a positive, an amplifying feedback. This makes the warming even stronger than it would be if there was no ice, if this feedback didn't exist. So this leads to a phenomenon called polar amplification. Which is that the global average temperature rise by the end of the century under sort of business as usual might be sort of 3 degrees C, sort of for the whole world, the average. But in the high latitudes, like in the Arctic, which is being clobbered most particularly today by this ice albedo feedback, the warming might be 8 degrees C. And then in the tropics, where there is no ice to be seen, the warming is less. So the average is sort of the combination of the extreme warming in like Alaska and Siberia and northern Canada, and then the less intense warming in places where there is no ice albedo feedback. So this is a pattern you can already see in the climate records today. The rate of warming is much more intense in Alaska than it is here. Actually, I saw a map of the temperature trends over the last some decades. It was part of the IPCC scientific assessment report. And the if you zero in, you find Lake Michigan and zero in on Chicago and check out that particular pixel, it hasn't really warmed much at all. It said 0 trend for the city of Chicago. So we haven't experienced much here, but people living along the North Slope, and in the Arctic, are temperature changes are much more noticeable, and that's because of this ice albedo feedback. Now the Southern Ocean, the Antarctic Ocean, is kind of a funny thing. The temperatures actually in the interior of Antarctica have gotten cooler over the last couple of decades. And then the ice that sort of fringes Antarctica, the sea ice, hasn't really melted much in the last few decades at all. But then just a little bit further away from the South Pole on the Antarctic Peninsula, which is this spit of land that sort of shoots up toward South America, there it has warmed more than any place on Earth. So the South Pole is kind of a weird thing. It's thought to do with the ozone hole. Ozone is particularly impacted by freons. We'll talk about ozone and freons and stuff in a couple of weeks. But ozone is a greenhouse gas, and so you change something about the dynamics. It's sort of still kind of not real clear exactly what's going on. But so far, anyway, the changes are much more intense in the Arctic than the Antarctic. So the ice albedo feedback is sort of a selective thing. It only affects some parts of the world and not others. But there's another positive feedback that affects every place. And if it wasn't for this other positive feedback, the whole issue of global warming might not be an issue. You'd be probably sitting in a class about the origin of the universe or something right now if it wasn't for this other feedback. And this is a positive feedback that's driven by water vapor. So you can read, if you read, I don't know, the Wall Street Journal or something like that, the idea that water vapor traps more infrared energy than CO2 does. And that's a true statement. So, but if you hear Glenn Beck or somebody like that say this, they'll say, so obviously we shouldn't worry about CO2, and then they'll go on to tell you that CO2 is not a poison and all kinds of other stuff that's sort of irrelevant to the issue. But the statement that water vapor traps more infrared than CO2 does is correct. That's a true statement. So the question is, if that's true, then does that mean that we don't have to worry so much about CO2? We should instead worry about our lawn sprinklers or something like that. And the answer to that is that there's sort of two parts. The water vapor in the air is controlled by the hydrological cycle, by the air rising up in some places as it undergoes convection, and when it rises it expands, and so it cools, and so the water condenses out, and that's where you get all this rain that we had last night. So the water vapor in the air is actually controlled by a nice negative feedback we can write. So in this case, the variable that is being fed back to is water vapor. The amount of water vapor in the air is sort of our state variable that we're applying a feedback to. And a perturbation, that could be like a lawn sprinkler. Somebody runs a sprinkler on a dry day, and so you make a lot of water evaporate or something. You perturb the amount of water vapor in the air somehow. But if you do that, then there's this feedback loop of it rains more. Or on the other hand, if somehow you pulled water vapor out of the atmosphere and made the air drier, that would make evaporation happen more quickly. And so these provide a nice negative feedback that fairly quickly control the amount of water vapor in the atmosphere. So if you run a sprinkler and it makes a lot of water evaporate, you're not causing global warming because the water will just rain out next week or something like that. But water vapor is a greenhouse gas, and so water vapor itself feeds back to the temperature of the Earth, and so we can write that this way. Here's temperature as our sort of state variable, and we'll have a perturbation to the Earth's temperature, so this could be from CO2 concentrations or other greenhouse gases in the atmosphere going up. Or it could be you perturb the climate by dialing up the sun or making the sun cooler or changing the albedo or whatever. So perturb the temperature, and the vapor concentration increases with increasing temperature, because that's just what water vapor does. The concentration of water vapor, the saturation amount of vapor pressure as a function of temperature is this very strong function of temperature. So warmer air, I mean, the way you always want to say it is that warm air holds more water vapor than cold air, and that's kind of true, but it's more like just warm holds more vapor than cold. It doesn't matter about the air, it's just a question of what the temperature of the water is. You could do the same thing in a vacuum. We talked about this before, that the amount of vapor just depends on the temperature of the water in the system, and it's not like it's a property of the air. But you warm it up, and you can hold more water vapor in warmer atmosphere than in a colder atmosphere. And so you perturb the temperature, say you warm up the temperature. That means you can put more water vapor in the air, and water vapor is a greenhouse gas. So then this is a positive feedback. So if we sort of write a recipe for this, we'll add CO2 to the air. The temperature rises because the CO2 traps infrared, and it's like putting a grape on the drain of the sink. It makes the water level in the sink higher, preventing energy from escaping. You make the temperature of the earth higher to balance. So now you got more water vapor. And so then the temperature goes up even more. So if the temperature goes up even more, then you could imagine this allowing even more water vapor and the temperature going up even more, and then more water vapor and more and more and more. And you may wonder, you may ask yourself, where does this end? How does this ever stop? There are conditions where this loop doesn't stop. That's called a runaway greenhouse effect. So how does that work? And is that going to affect us? The way to look at this is to draw what's called a phase diagram. For water. And so there's going to be pressure as one thing that that's going to be one axis of this plot. So one of the dimensions that we're going to think about is the pressure, and the other is the temperature. So at different pressures and temperatures, water is stable in different forms. And so the boundaries between these different forms, they look like this. So if the temperature is pretty high and the pressure is pretty low, all we're going to have is vapor. So this is where vapor only. If we keep the temperature sort of high and put it under higher pressure, then we start getting this field up here, which has vapor plus liquid. And then down here at cold temperatures, this is vapor plus ice. So this axis pressure is actually the pressure of water vapor. So this part of the curve right here, you've seen that before. That's just what we drew a second ago, the pressure of vapor as a function of temperature. It sort of goes up like that. It's how much vapor you can have before you start to condense. It's a function of temperature. As the temperature goes up, the amount of vapor you can have before it condenses goes up. So this line right here is, we called that before, the 100% relative humidity line. Everybody understand what that diagram kind of means? Yeah.
Could you get, earlier when you were talking about water vapor and relative humidity, you were talking about 110 and 120%?
Yes.
Does that mean that it is already condensed, or can the atmosphere hold more than?
It can, but not for very long, not forever. So let's say you have 100% relative humidity, and you calculate the energy of all of those waters there, and then you allow some of that water to condense and make liquid, so it goes down to 100% relative humidity, and you calculate the energy of those waters in the liquid and in the vapor phase, and that will be a lower energy state than the 120% relative humidity. So it wants to be there. It may take a little while to get there. If the air is very clean, there may be no little droplets to sort of condense onto. So you can keep more in the air than really wants to be there. But so that's where cloud seeding comes in, that idea of making it rain by putting silver nitrate in the sprinkling in the clouds. It allows the droplets to start forming. So you have to start out with air that's got more water vapor in it than it really wants. That is more than 100% relative humidity. And then the theory was you could try to make it rain. It never really worked. But so it's not impossible to have 120% relative humidity, but it's just not as happy that way, and it wants to condense. So it's just a question of, where the lowest energy is. All right, so on this phase diagram, we're going to do a sort of thought experiment. We're going to start out with a planet with no water vapor. And we're going to calculate the temperature using something like the layer model or some climate model where you balance the energy coming in and going out. And the temperature, let's say it's right here. So that's point number 1. Let's clean this up. So that would be that would be 0% relative humidity, no water vapor in the air. But say there's a lake or an ocean or something like that sitting there, and if you've got 0 relative humidity, then the water wants to evaporate. It wants to be at 100% relative humidity. So step 2, evaporate water, and then calculate the temperature. Again, as you put more water vapor in there, water is a greenhouse gas. And so as the pressure of the water vapor goes up, the temperature sort of rises. So sort of step 2 is kind of going like that. You put more water vapor in, the water vapor causes the planet to warm up. Step 3, happily on Earth, you hit something like 100% relative humidity and it rains. So this is sort of as far as you can go on this plot starting from here, because you don't want to put more water vapor in the air than 100% relative humidity. You can do it for a little while, but not forever, because it'll rain. So the thing that prevents the runaway greenhouse effect on Earth is we hit this liquid phase boundary. So it starts to rain. Mars starts out colder, and when you do the same experiment, it hits the phase boundary in the snow area, the ice. It hits the ice field, and so it snows. Same thing would happen here in the wintertime. You'd start out from a colder base temperature. So the poster child for a runaway greenhouse is the planet Venus. Venus, close to the sun, and had a high temperature. It would have had a high temperature sort of initially, and then they think, planetary scientists think, that there was as much water on Venus as there was on Earth. Venus is the same size as Earth, close in orbit. It's really truly our sister planet. Mars is smaller and seems like it's different in some ways. So Venus is like us, only different part of the solar system. And it starts out a little hotter, and the way it goes on Venus, it never hits that liquid field. That's the runaway. So what actually happened on Venus is the oceans boiled all into the atmosphere. So this runaway happens until you run out of water, basically. You just throw all of your water into the air. And so if this is the planet and here's sort of the atmosphere of Venus, there is ultraviolet light from the sun that comes and sort of doesn't penetrate very far down into the atmosphere. It's really nasty stuff that would just fry you to a crisp if you were up there. And so if there's water vapor that gets high up in the atmosphere, it gets split into atoms. It just gets blasted to smithereens into hydrogen and oxygen atoms. And the hydrogens are small enough that they move quickly enough that they escape to space. So a runaway greenhouse effect is a one-way street. Once you get water into the upper atmosphere of a planet, like happened on Venus, it's gone forever. You lose the hydrogen and you never, ever, ever get it back. So on Earth, if we look at the temperature of the atmosphere as a function of height, the temperature drops as you go up because of convection and moist, the moist adiabat, moist convection that we talked about. Eventually, it starts to rise again in the stratosphere, but there's this, the coldest part of the atmosphere is called the Tropopause. It's sort of where airplanes fly. It's the boundary between the troposphere, where all the weather is, and the stratosphere, which is sort of different. And this tropopause is like a cold trap. So any water that evaporates at the ground is not going to get carried up into the upper atmosphere where the UV is up here, because the air is very cold there, and it's going to make the water condense out, make it rain or snow. So the water is all down here at the ground. There's the ocean, and there's this UV up here. And if this water ever got up there, it would be toast. It would be lost forever. And so the thing that is preventing this from happening on the Earth, that's preventing us from losing our water, is this sort of a cold trap. Of the tropopause. And so if you look at those pictures of Earth from space, the atmosphere is so thin you can barely even see it. And so you look down at the planet and you see these vast expanses of ocean, and all that water has to do is to get 20 or 30 kilometers up in the atmosphere in vapor form, and it would be lost. And yet the planet is 4.5 billion years old, and that has never happened. So this cold trap of the troposphere is all that's protecting the water on Earth from just being lost in this runaway greenhouse effect. It's astonishing to me that it hasn't already happened in some way. So with that chilling thought, we'll stop and come back on Monday.